are recording. Yeah, so I'll just revise a bit of the earlier stuff, cross ratios, pencils, a little bit of that. I'll go a bit fast, but like if anywhere you have any issue, feel free to just ask. Like I'll be glad to clarify. So essentially, this is how we define cross ratios. We have 4 points: x, y, and like this is the cross ratio a b x y. This is just xa by xb divided by is to ya by y. Yeah, this is the definition. This is the ratio, and we have a similar definition for a pencil of lines. So we have a point P and we have lines x, y, a, and b passing through it, and we can define a cross ratio similarly. Just like we have the sign, we have the sign of the angle between the lines respectively. So x comma a sine of uh, x comma b is to the sine of angle y comma a y comma b. Right. So this is probably what you have done this before, and these lengths are directed, so you can get negative as well. So for example, the most important one is when this is -1. Right. And the entire reason why we define this stuff is because we can do what is known as a projection. So we have a point P, we have 4 lines, we have 2 other lines cutting it. If say this is A, B, C and D, and this is like W, X, Y, Z, then the cross ratio ABCD is equal to the cross ratio WXYZ. This is sort of the sole purpose why we define the cross ratio. This is a length chase sort of condition which we can write in like half a line. That is kind of the purpose why we define it. But yeah, of course, it goes into a lot more depth than this. So yeah, we can define this stuff for a circle as well because the angles in a circle are nice. If you have a circle and we have like 5 points, so one of the point is P and A. This is A, B, C, and D, and there is a line cutting the circle. Say this is W, X, Y, and Z. Then the cross ratio ABCD is equal to the cross ratio WXYZ. So essentially, this point, what it means by projecting is that this point A goes to W, this point B goes to X, this point C goes to Y, and the point D goes to Z. This is sort of this is how you think of it, and like once you get more comfortable, you don't really need to do it. You can sort of feel what is equal to each other, but yeah, when you're beginning, it's probably good to do it that way. Yeah. So here's the first sort of place where this is very useful is when we have what is known as a complete quadrilateral. So essentially, just take any quadrilateral ABCD and extend the sides to meet each other. So we have AB cap CD and AD cap BC. Call this P, call this Q. And yeah, this is quite common. Like call this like X. This is quite a common thing in this, like this configuration does appear a lot. Like in other configs as well as like on its own. Call this like y. And why the reason why cross ratios are helpful here is because you have sort of these 2 points where you can project through. So you take the cross ratio q comma y and like b comma c, and you have 2 points where you can project. You have point p and you have point x. But okay, notice like when you project through p or x, q remains constant. So you are projecting from this line to this line. Q sort of remains constant, but C goes here and D goes here. So that is kind of why this is helpful, because you can project through P and like, okay, I'll just name this one. This Z. So you can project through P and you will get Q will remain there. Y will go to Z. D goes to B and like C goes to A. Whereas you project through X, Q and Z still are in the same positions, but D goes here, D goes to B, and like, wait,
In the first one, I think it should be A or B.
yeah, it's X. This is projecting to X, and this is project. This is projecting through. Yeah, this is projecting through. This is P. Yeah, if we project through P, Q and Z sort of remain in the same places, but now D goes to A, and like C goes to B. So essentially, in one in one projection, B and A get interchanged. So you can use this equality to show that QZEB is minus 1. Yeah. And this is extremely useful. This idea of projecting through 2 points is like very useful. It does take a while to get comfortable with, but yeah, once you are, you can like kill a lot of problems. So there are a few other configurations. Okay, so in this config, you take any 4 collinear points. Okay, there is a bit more. This, this, yeah. You can check that in this config, any 4 collinear points are in a harmonic bundle. So harmonic bundle is like -1. Like you have QD, you have these 4 are in a harmonic bundle, and like similarly, you can get that these 4 are in harmonic bundles, and you can project from here, you can project from here, and you can basically do this for every other pair of points, set of points. Let's move on to the second sort of thing, and this is sort of introducing the point at infinity. We have a line segment. Well, we have a line. A and B are 2 points on it. Yeah. M is the midpoint, and P is what we define as the point at infinity. So it's sort of, if you just keep going along this, it will come sometimes. And like the reason why we define is when we do stuff. Okay, so when we do stuff using transformations, like some mappings, some points they just like go to infinity, sort of like when you have a graph, you can have asymptotes. That is sort of why we define the point at infinity. It's also quite useful because any two parallel lines will converge at the point of infinity, right? So they won't obviously converge at any finite distance. They'll converge at the point at infinity. And sort of, if you're working a diagram, it might get a bit messy to denote the point at infinity. Just instead of writing here, you can just like make it dotted and make it here. This is what I do. And you can check. The other useful reason is because this cross ratio turns out to be -1. like you have MB by MA is just MB by MA is -1 is to P alpha a P infinity B upon P infinity A is like 1. So you get -1. Like, by the way, this is -1 because we are using directed segments. So yeah, you can use this. Okay, well, not this, but there is a third configuration. These are just like common configurations which show up. And when you see, so for example, when you see a complete quadrilateral, when you see this configuration, it's sort of a direct idea to use projective. Well, not always, but like 90% of the time. Yeah. A third thing is sort of like this. You have points A, B, C, D in a circle such that like C and D, such that CD, the tangent at A and tangent at B, meet at some point T. This quadrilateral here is no, it's a very special quadrilateral because it has like a bunch of properties, and it is known as a harmonic quadrilateral. Cyclic, it has to be cyclic. That's otherwise we cannot define a cross ratio. But yeah, the idea is that here the cross ratio ABCD turns out to be -1 as well. Because you have 2 points to project through. So you want to project through A and B because the problem is sort of symmetric in A and B, and you want to project onto a line. So okay, so first, instead of defining a new line, you should probably try to project onto a line which is already defined. In this case, it would be CD, and you take like ABCD and you want to map it to CD. So if you take, okay, B goes to this point, the intersection, I'll call it X. C goes to, C remains there because already on the line, and D also remains there. But A goes to T because, like, how do you define, where does A go? A is just like, if you take any point X, it would go like AX cap CD, right? So you replace X with A, you get like A cap CD. And like if you sort of take the limit as X approaches to A, you will get the tangent. That is also how we kind of define the tangent. More of a calculus way, but it does work here. So like this cross ratio, this is equal to A X, C goes C and D remain there. And if you project it through B, you will get this.
Shouldn't that be T?
Yeah, it is. You get X. So essentially, like T and X just get interchanged. C and D remain in their own places. So yeah, you have this equality, and whenever you have this equality, you can just write out the ratio or just like remember that it gives you minus. Yeah, so these are three sort of very common things that you will get to see in projective geometry. And okay, even when you don't see it, they might be sort of hiding in the configuration. You just might have to explore. So yeah, now that we have done some basic cross ratios, well, okay, this is just like a speed run because I think there was already a class on this. I just wanted to sort of revise this stuff. Um, let us do some problems. I think we can do 1 or 2 problems on this. Uh, okay, so shall I give an easy one or a hard one? Hmm. Let's start. Okay, yeah, let's start with this. Mm. Okay, just a second. Yeah, wait, how do I paste this problem? What? Yeah. Can you see the, okay, no, the problem is not there. What? Okay, yeah. Yeah, is the problem visible now?
Yes.
Yes.
Okay, so you have a triangle. Okay, yeah. C, and R is the external angle bisector. So we extend it, would be sort of like this. So this angle is equal to this angle. P and Q are the feet. Okay, this is, yeah. P and Q are the feet of perpendiculars from A and C. Q. Okay, I'll just shift the figure a bit. Yeah, hope it's better now. And we want to show that AP meets if sorry CP meets M and this is N. We sort of want to show that these things concur on AC. Okay, so yeah, so this is you have the complete quadrilateral sort of baked into the figure, right? You have MNCA, you have NC cap MA, you have MN cap AC, and uh you also have the external angle bisector, which sort of motivates us to draw the internal angle bisector as well. I mean, they are sort of in a pair, and it looks like the internal angle bisector passes through this point. And okay, if if you work backwards, you will realize that that's true, because like if PQ meets Mn at AC, then this thing has to be a harmonic quadrilateral. So this point, and this point has to be in a harmonic conjugate. So that would imply that this is the angle bisector because of the internal angle bisector thing, internal external angle bisector being in a harmonic conjugate. I think this was covered in class last time. So yeah, so we know that this is true. In fact, proving that the angle bisector passes through the intersection would finish. Well, what do? We want to prove that, okay, alternately, we could just prove that this ratio is, yeah, we could alternately just prove that the ratio of this cross ratio is just 1. Call this y. We can prove that we want to show that x comma y and a comma c, they are like -1. This is what we want to show. And we want to project this in some way, right? The one obvious thing for projection is just this point, I'll call it z, because you can project and you will get that if you project this cross ratio through z. So if you project through z, you will get that y goes to this intersection point. Let's name it something else, w. X remains there because it's on mn itself. C goes to m and a goes to n. So x remains there, y goes to w, a goes to n, and c goes to n. Right. And we want another point to project through, because, well, that's kind of what we did in the harmonic thing, right? Well, now we are stuck. We don't know what else to project through. So now you would ideally sort of step away from projective for a while, look at some more synthetic stuff, like maybe angles. And if you do that, you will realize that this angle is 90. This is the external bisector, this is the internal bisector, so the angle has to be 90. And this is sort of this means that AP, BZ, and CQ are parallel, right? And we want to use this. This was essentially unable to use this perpendicularity condition, right? How do we use this? Well, one thing would be to look at, like midpoint formula or Thales theorem or whatever. We could, what we do is do it in a more projective way. So what we do is we define P infinity to be the point at infinity along these lines. They are parallel, so they meet at the point at infinity, and we project through the point at infinity, because sort of because you we project onto the line mn. So x and y goes to the same place, and when we projected through z, a and c sort of did this zigzag thing, and if you project to the point at infinity, they don't do this exact thing. Right. So if you project to mn, then okay, wait, we should project it onto this PQ line, the external angle bisector. So if you project through that, you will, like, if you let this be like x dash, you'll get that x goes to some x dash. We project through the point at infinity, x goes to some x dash, y just goes to w again. A goes to P and B goes to Q. And if you sort of project this through Z again, so you want to project this thing onto this thing, you will get that X remains there. Like, you have M goes to P. Okay, wait, we have Y first, right? Y goes to B, M goes to P, and this goes to Q. Wait, Y goes to B, this goes to B. So because you have this equality, like x v p q is equal to x dash v p q, you're done. X is equal to x dash. That is what you wanted. And, like, yeah, this is a common idea. This is decently common idea. You want to project through two things. One of the things where there is this zigzag sort of pattern, and the other thing where there's this straight line sort of pattern. So you get the equality. Yeah, so shall we do another problem or do we just move on to something else? Well, we have to probably cover some theory, some more theory rather. Yeah, poles and polars, right? I think I take it that this is new stuff. So yeah, I will just do some new theory. We have a circle with center O and we have a point P. And what we define is we define its inverse with respect to the circle, call it P dash, and we define a line which is which is perpendicular to OP, and this line is like the pole of P. We just it should be ideally it is the pole of P with respect to this circle W, but we just call it the pole of P. Is this clear? This is sort of the definition. P is the inverse of, so if you perform inversion at O with radius OW, then like you will get P dash and you'll get a line passing through P dash. That will become the pole. The reason it's useful is because of a theorem known as Lahayer's theorem. So like suppose this is a circle, this is O, this is like P, and this is some point Q, and like the pole of Q to the edge. This is Q, and like this is P dash, and this is Q dash. These are the respective inverses. The pole of P dash, the pole of Q would be sort of like this. So what the theorem says, the theorem states that P lies on the pole of Q. Q is the same as saying that Q lies on the pole of P. So there's this sort of duality, right? You can exchange P and Q and nothing changes. And yeah, so this is not very hard to prove, but yeah, this is a very nice theorem. Like suppose P dash happened to lie on the pole of the suppose P lies on the pole of Q. So like the pole of Q is just this pink line, and then you have P dash, you have P lying on it. So if you want to define the pole of P, you have to first invert. So suppose like P dash is the inverse. This is P dash, and you want to define a line through P dash, which is perpendicular to OP, and this is the pole of P. And you want to show that Q lies on the pole of P. But the idea is that when you invert 2 points, they form a cyclic quadrilateral, right? So we know that P dash, Q dash have to be cyclic because of the property of inversion. OP dash into OP is equal to OQ into OQ dash, so they have to be cyclic. And that implies that Q lies on this line. So Q lies on the pole of P. And this sort of may seem trivial, like it's just an inversion. This is not even projective, right? This is just angle chasing stuff. It is very helpful. this is like extremely helpful, and you should sort of get the intuition behind this, because this is where we bring the projective stuff. This is where we bring cross ratios into the picture. Oh. Yeah, this is point O. You have P and its inverse P dash. So when we define the inverse, what you could do is just drop tangents. So if this is P dash A, and this is P dash B, you would get that these 3 points are collinear. And this is also not projective. You just use some, well, you could do a lot of things, but like some similarity stuff just finishes this. I'll leave it to you to prove it. But yeah, so what you can do is you can define if you take P dash, then you can define the pole of P dash in a nice way, which is this. And if you sort of go back to the third configuration we had, looks sort of similar because we have two tangents there as well. So that is sort of an intuition why projective would be even helpful here. The idea is if you take any point on the pole of P dash, say like Q, right? You do this, and from the earlier theorem, x, y, you have x, y, q, comma, p dash. This is a harmonic conjugate. This is a harmonic bundle, rather. And you know that q lies on the pole of p dash. So from the theorem we just did, Lahair's theorem, you would have that p dash lies on the pole of q. So if you sort of make this, then yeah, this would be the pole of, this would be the inverse of q. And this is sort of helpful in like inversion stuff, because, well, sometimes you don't really know how to define the inverse of a point, especially if it is like an awkward point. But yeah, this way you can. What? Yeah, this this is q dash. This is 90 degrees. And another thing, if you note, we could make use of this harmonic bundle even more, because if you draw another line through P dash and it meets here, say like at W and at Z, and it meets AB and at like L, then from the previous theorem from like config 3, you would have that W comma Z, that this cross ratio is -1 as well. So what you would do, so if you had like 2 points which form a harmonic bundle with P dash, then it sort of fixes the pole of P dash. And that is very useful, as we will see in the problem we will do just now. Right. So this is what poles and polars are essentially about. You look at, so yeah, I mean, you do need to know a little bit of inversion for this, but it is not that like hard. We should do a problem on this. We should do a nice problem. Um, Let me look for it. Okay, yeah, this. By the way, if anything is not clear, if you have any doubt, you can ask me. I'd be only happy to explain. Yeah, this is our next problem. Okay, we should probably, yeah, we have a triangle ABC and an incircle. And the contact points are defined as D, E, and F. Okay, let X be a point on BC. And let the tangent from X touch the incircle in some. Okay, I'll just make the X. I'll make X a bit closer. Yeah, let's suppose this is X and this touches the incircle at point Y. And it meets EF. Okay. DE meets EF in Z. Okay, this is EF. This point is D. This point is Y. Yeah. So you want to show that IZ is perpendicular to AX. I want to show that IZ is perpendicular to AX. And sort of when you have a perpendicularity condition, I mean, angle chasing is much more motivated. But in this case, there are like a bunch of things which make projective much nicer. One thing is like you have the tangent thing. So you have something which is like primitive to projective geometry. Second of all, you can actually you can deal with right angles using projective, because when you had this when we did pole polars, if you just define these cross ratios as -1 and you define the line, we get a 90-degree angle for free. So that is what essentially motivates us to use pole polars. And yeah, so the sort of one idea is that if you could prove that this intersection is the inverse of Z, then you are done, right? Because the inverse of Z, and like if you can prove that this is the pole of Z in the incircle, then you're done, because IZ would be directly perpendicular to AX by the definition. So, well, if you want to show that AX is the pole of Z, you want to show that A lies on the pole of Z. So, by Laplace, if you show that Z lies on the pole of A, then you should be good, right? Well, you have to show that both Z and X lie on the poles of A. What's the pole of A? Well, if you look here, you have the tangent to the incircle touching it at like F and E, and you have a line passing through EF, and you know that Z lies on EF. So this is just the pole of A. and therefore Z lies on the pole of A. So this thing we can take off. We want to show that X also lies on the pole of A. So sorry, Z also lies on the pole of X. Okay, hold on. Okay, yeah. Yeah. You want to show that Z lies on the pole of X as well. Z lies on the pole of X. And what is the pole of X? It is like, this is a tangent, this is a tangent. So it would be this. And by definition, Z also lies on dy. So this is also ticked off. So Z lies on the pole of A and Z lies on the pole of Y. This implies that A lies on the pole of Z. This implies that Y lies on the pole of Z. So X lies on the pole of Z. So AX has to be the pole of Z. And therefore, by definition, we get this perpendicular. And we are done. So it's sort of like this problem. Well, it's not just completely immune to angle chasing. You could probably angle chase some stuff, but it is very difficult to angle chase this. So that is sort of that is a neat part, because a lot of projective problems you just can't approach with angle chasing, or it just takes a ridiculously long time, or it's a very tricky angle chase. Let us move on to some. Shall we do another problem on this?
Yeah.
Let's do one on cross ratios, because I have one on cross ratios. Also, like, if you have seen any of the problems, well, I don't think any of you would have seen any of the problems, because they are like random problems. They are not from any famous source. But if you have seen any problem, just tell me. I'll give another one. Uh, let's go somewhere else. Yeah, this is a problem. Shall I give Shall I give you some time to try this? It's a nice problem. It's a nice problem.
Yes, please give time.
Okay, I'll wait for like 5 minutes, so maybe till like 6:53. Well, in the meanwhile, if any of you have any doubts or something, you could let me know. I'll be back in a second. Okay, so let's just like read the problem. I'll make the diagram. You have a circle ABC. You have the circumcenter, which is a bit weird. You don't usually see like circumcenter almost always
Wait,
means that.
someone is saying don't make the diagram. Give them 5 more minutes.
Okay. Let me just make a triangle. Also, shall I do more problems or shall I cover more theory? Like, okay, there is not much theory left. So after this, we will be doing brocards. And after that, it is problems, but brocards might take it will take a while. So before that, shall we do another problem, like after this? Or shall I just do this and then move on to theory? Like, I mean, obviously, doing problems is more interesting, but like, I have to get theory done. So, all right, I'll make the diagram now. Some theory and some problems. Sure, I think okay, then I can do another problem after this. It depends how much time we are left with, because the class is still only 7:30. I don't want to extend it to like 8 o'clock, 8:15 or something. We have O, and D is a foot of altitude from A. Let CO meet AD in E. And let M be the midpoint of AE. Okay, this is M. Let MO meet BC in G. Okay, this G. And let F be the foot of perpendicular from C to AO. We want to show that BOGF is a cyclic quadrilateral. So something like this. Right. How do you do this? Any progress? Do we have any progress? Did you get anything on this? F lies on ABC. Okay, sure. Yeah, that is. Hmm. Okay, no, that is not correct because this angle is 90 and not the other angle. Like this angle is 90, not this angle. Like AB, like angle ABC is not right angle. So yeah. Okay, so essentially how you approach this sort of problem is that you don't just look for harmonic harmonic conjugates or harmonic bundles, because you want to show something is cyclic, right? It is a very angle chase condition. So you do want to use angle chase at least a bit. You can't just do projective and just finish the problem. You need to do some angle chase. So what angles do we pick? We have this angle, which is not very good. If we want this angle, we would have to define a new line. So we will not do that in the beginning. This angle is nice. And the other angle, which is arguably better, is this angle, angle OBC. The reason is that this is equal to angle OCB. So we are using half of the point of defining O. Like you are given O in the problem, so you need to use some characteristic of O, and this is one of them. This doesn't fix O, but this is sort of this uses O, right? You want to show that this angle is equal to this angle, and you know that this angle is equal to this angle. So if you could show that angle, okay, yeah, this point is G. I'll just write it in a different column. Yeah, this point is G. This one. So if you could show that angle GFO is equal to angle GCO, you would be done, right? You want to show that this angle is equal to this angle. So another very natural thing to do is if you extend this line, if you extend this line and let this meet in some new point, call it yeah, or we haven't used x, right? Call it x. So you want to show that this angle is equal to this angle. So that is equivalent to showing that this is cyclic, right? This is essentially the process of thinking backwards. You would want to show that if you let this be y, then you want to show that um, like x, y, f, and c lie on a circle. And we already know angle YFC, that's just 90. It's given to us by the problem. So it would be equivalent to showing that this angle is 90 as well. Right. And then you stop and you have nothing because what do you do from here? Like, sure, you have this angle 90 as well, but how does that help you? Well, let us look at what we haven't used, and it is this midpoint because AE is random and midpoint is even more random. So you think how do you use midpoints in geometry? One way is you define the midpoint of something else. So if you define this midpoint, you would have midpoint theorem and a parallel line. Sure, that's nice. What else do you do? You can use the power of a point concept. So if you can get a circle such that the power of m with respect to is ma squared, then it is also equal to me squared. So you can get nice things done. Often it would imply that AE is tangent to the circle. But there isn't really any obvious circle, right? There is no obvious circle, so yeah, that is not something we can do very easily. The third thing, and probably it is this is where sort of you start thinking about projective because of the property we did, the midpoint wala thing. Yeah, this one. You can make use of midpoints by defining the line at the point at infinity, and you get a harmonic bundle. This is yeah, you would get a harmonic bundle. So let us just do that. We define the point at infinity, sort of here. Say it is here along the line AD, and you want to project through something, right? You have you honestly don't even have too many options because O is the obvious choice to project through because we have MO defined in the problem, we have AO defined in the problem, we have EO defined in the problem as well. And what about P infinity O? It is just a line through O which is parallel to AD. So yeah, it is parallel to AD. And you want to project it somewhere, right? So, okay, projecting it onto BC is also quite natural because you have already defined AO cap BC. The problem has defined EO cap BC is literally just C. And you have MO cap BC also defined as G in the problem. This is like point G. Okay, hold on. I'll just make the lines a bit thinner so you can actually see what's going on. You have this defined, you have this defined. This is also defined. This is just point G. And what about P infinity cap BC? That is the midpoint of BCM, because OM, okay, not M. Is M already defined in the, yeah, it is. Call it like L, the midpoint of BC, because OL is perpendicular to BC, right? Because AD is perpendicular to BC. And yeah, you have this point, this point, this point, and this point in a harmonic bundle. So let's write that down. You have L, EO cap BC we defined as Y. Okay, not LY. L and yeah, LG, EO cap BC is Y and C -1. And sort of, okay, we have a thing that is -1. How do we use it? Well, if you look at the figure carefully, what did we introduce? What stuff happened when we defined L? We got a 90-degree angle. So yeah, we made this a 90-degree angle, and we already have this as a 90-degree angle. So yeah, complete the figure. You get an orthocenter. Call this Z. You get an orthocenter. Well, almost. You get an orthocenter configuration. Yeah, you get this as an orthocenter, but you know that like you want to show that this is what you want to show, right? This angle is 90. This is what you want to show. That is essentially the same as showing that this is collinear, right? Because we get that this point is the orthocenter. How do we do that? We want to make use of the cross ratio, right? We have LGYC is -1. So sort of look at the harmonic quadrilateral OXFZ. Well, it's a quadrilateral. It's not harmonic. You can think of it as a complete quadrilateral. Like if you sort of extended this and it met it somewhere, it would be a complete quadrilateral. But the idea is that you have this in a harmonic bundle. And if you look at the first config that we explored, so it was this one. Yeah, there also this, and this were in a harmonic conjugate. So if you complete the figure, this where did it go? Here. So if you sort of complete the figure, it would imply that this is in a line. And that is what we wanted to prove. And we are done. This is a very instructive problem because you can work backwards. Everything is motivated, but it's a nice problem. It's also not very famous. But yeah, is that clear? Any doubts? Okay, fine. Let's move on. Let me see if there's any other problem I can give. Hmm. Let's do this problem. Okay, no, we should probably do Brocard first. We don't have much time left. And that is quite an important part of the theory. Okay. Brocard's theorem. So take a cyclic quadrilateral ABCD. Well, we take, suppose this is A, this is B, this is C, and this is D, right? Yeah. Suppose the opposite sides intersect at P and Q. Let this be P, and let AC cap BD be Q. Right. And let's suppose the diagonals intersect in R. Finally, if O is the center of the circle, then then R is the orthocenter of POQ. POQ. And if you look at this result, it does not look like it has. Okay, there is a complete quadrilateral which is baked into the statement. But if you didn't know projective and somebody gave you this and told you to prove it, yes, you would not question it. This looks angle chaseable. You have orthocenter, and that's quite a basic thing. That's probably the first thing people study. And this does not look like we haven't introduced anything projective. I could have just given this to you on day one of geometry. So why do we need projector? Why do we need such a powerful technique to kill this? More importantly, why does projective why does it serve any purpose here? The idea is again the polars thing that we did. We get if we look at harmonic bundles, and if you look at lines through them, you get this 90-degree angle for free. Right. And orthocenter config is all about 90 degrees angle. So yeah, it probably would be useful. So yeah, the key idea is to show that, okay, yeah, you want to show that R lies on you want to show that PQ is the pole of R. That is sort of the main idea, right? Because then you would directly get by definition this perpendicularity, and you could think on similar lines to prove the other 90-degree angles. How do you show that? You want to show that PQ pole of R, right? How do you show that? This would imply that P lies on the pole of R and Q lies on the pole of R, and we could use Lahayer's, I'm just writing LH, and we could prove the opposite thing. So if we could prove that R lies on the pole of P and R also lies on the pole of Q, then we would be done. Okay, so what is the pole of P? What is the pole of P? Well, we want harmonic bundles, right? So if we define this thing, call it like X, and if we define this thing, call it as Y, such that these form a harmonic bundle and these form a harmonic bundle, then we could say that XY is the pole of P, right? But if you look at the complete quadrilateral figure, that is sort of essentially what we had. We had this thing forming a harmonic bundle. We had this thing forming a harmonic bundle, and it happened to pass through the intersection of diagonals. So yeah, you could use this figure specifically. Okay, let's just write the thing. We should probably just write the cross ratio case, right? More specifically, if we let if we redefine x and y, so like if suppose we take let x be xr cap AB and y equal to xr cap AC, QR cap CD, then you would want to show that these are harmonic conjugates, harmonic bundles. So yeah, you have Q, comma R, X, comma Y. You want to show that this is -1. So you want to project through something, right? And well, okay, if you project through project through P, so R sort of goes to this thing, call it Z. Q remains there. You want to project it to AC, right? So Q is already on AC. R goes to Z. Where does X go? X goes to A and Y goes to C. So you have that. But we already know that these 4 points are harmonic because you look at the complete quadrilateral, right? Well, you could also say that these are collinear lines and any 4 collinear lines points would be harmonic. But yeah, this turns out to be -1. So essentially, you showed that xy is the pole of P, and because R lies on xy, R lies on the pole of P. And P and Q are symmetric. You don't need to really prove the other. You get it for free. You get R lies on the pole of P, R also lies on the pole of Q. So PQ is the pole of R, and therefore OR is perpendicular to PQ. Yeah. This is only one part of the thing we want. We want to show that R is the orthocenter, right? You also want to show that, say, you want to show that this angle is 90. This angle is 90. Yeah. So this is also just pole polars, right? You want to show that PR is the pole of Q. So this is just like very similar stuff. You want to show that PR is the pole of Q. So you want to show that P lies on the pole of Q, R lies on the pole of Q, and you can use Lahayer's to prove the opposite. So you want to show that Q lies on the pole of P and R lies on the pole of P, right? And if you look at the figure, Q lies on the pole of P. What is the pole of P? It is precisely XY because PA calculated PXAB is -1. X A comma B is equal to -1. And PYCD is also equal to minus PYC comma D is equal to -1. So XY is the pole of P and Q lies on XY by our definition. So Q lies on the pole of P. And we have Q lies on the pole of, right. Oh, where is, oh yeah. To get this 90-degree thing, you want to like, okay, yeah. Yeah, you get that Q lies on the pole of P, right? This is the pole of P. And you want to show that PR is like perpendicular to Q. Okay, yeah, okay. You want to show that OQ is perpendicular to QR. So you show that like you have like R and like you have Q. So like you want to show that Q lies on the pole of like R, but we already have that, right? We did that. Yeah, we did that. Q lies on the pole of R. So we get that 90-degree as well. And we are sort of done. Should probably make a better diagram. But yeah, is that clear. Uh-uh. Yeah, you have OR is perpendicular. You have OR is perpendicular to PQ, and you have like PR is like OQ is perpendicular to PR. That's like PR is the pole of Q, right? Because we know that we got that P lies on the pole of Q because if you look at this point, call this like L. No, wait, we already used that. Yeah. Yeah, call it like G or something. Then like you know that QG AB is like -1. G A comma B is equal to -1. And you also know that this point, call it like F. QFDC is -1 because they are like four collinear points and complete quadrilateral. They have to be harmonic. DC is equal to -1. So R lies, so like both P and R. So essentially just PR is the pole of Q. Q. So yeah, PR is the pole of Q. So by definition, OQ is perpendicular to PR. And that's the second thing we wanted. And yeah, two things are enough. PR. So yes, R is the orthocenter of POQ. Is that clear? This is a very nice idea because like whenever you have a complete quadrilateral and you want to make use of a 90-degree angle, you can always define like OR cap PQ. And like this doesn't even end here. There is even more stuff because I don't know if Mickle point has been completed, but yeah, this thing is the Mickle point of ABCD. And and there's this concyclicity, there's this concyclicity, all sorts of neat stuff. Is that clear? Like if you have any doubts, you should probably ask because yeah, this is like a very this helps build a geometrical intuition a lot. Okay, yeah. Okay, so we have like 10 minutes. We can do a problem. We can, yes. Let's do a problem this time. Okay, shall I do a problem or shall I cover Pascal's theorem? Because that is also quite important. Okay, sure, let's do a problem then. Let me look for a problem. Okay, this one. Mm, okay, go a bit down, right? Like here. Yep. This is a problem. Let ABC would be a triangle with incenter I. Suppose insert its tangent in this is we have reflections of the tangency points over I. We have the midpoint of BC. We have the intersection of BC with GH, and we want to show that there's a 90-degree angle, right? Okay, shall I give you like, oh, I really don't have much time. I'm not sure if I can give any time. I'll give like maybe 2 minutes for you to try. Like maybe just get down, maybe just draw a diagram and like you can like throw in ideas. I'll draw the diagram in the meanwhile. In center I and in circle. Okay, we want to draw the in circle. And like you will notice a lot of problems have in circle in them because, well, you have this tangency thing which is like very nice to deal with using projective geometry. When you study the in center config, you will also realize that projective is in almost every claim. So it's probably like it's better to do this well before attempting any other configurations. Well, even orthocentric configuration. So circle is tangent to E and F. Okay, we don't have B. Okay, we have I and the reflections. Okay, so obviously the reflection has to lie on the in circle and like it forms a rectangle as well. This is H. And we have GH meets BC at Q. That's this. This is point Q. Yeah, we want to show that IQ and IM are perpendicular. So M is like this. We want to show this with 90 degrees. Okay, so first things first. The reflection is not okay. The reflection is okay to deal with, but it would be nice if we could eradicate it in some way. So the idea is that you just reflect everything back in I. So G just goes to E. We are reflecting in I. So G goes to E, H goes to F. And the only thing, and sort of M goes to this kind of awkward point, call it N. And GH just goes to EF. The line GH goes to line EF. We have we want to show that like GH cap BC. Where does BC go to? Well, like if you reflect BC over I, you will get this line. If this is D, call this like T or something. You get this line. So this is just the reflection of Q, call it P. And you would want to show, so you would want to show that angle PIN is 90 degree, right? And here is where the reflection actually becomes good because you don't need N because angle PI, showing that angle PIN is 90 is the same as showing that the angle PIM is 90. Right. You can just discard. You can just discard n. So that's sort of the one good thing of reflecting in the figure. And you can also forget about Q, G, and H. Forget about this. This is a much simpler problem. You have, and you want to show that angle PIM is 90. You want to show that the angle is subtended at the center of the circle. So you can't really see a direct way of using poles and polars. So, well, that's that. You also, there is no very, like, you don't see a very obvious harmonic bundle. Right. Okay, sure. You have AE and AF, but you also want other tangents, right? So the idea is that you have AE, you have AF, you have this PT, which is by the way parallel to BC. So just define the other tangent. That is the sort of motivation of defining the tangent, right? It completes the configuration. It helps us identify some harmonic quadrilaterals, right? Make this, we have R. Let's call it R. So what do we have? We have that we have the tangent PT. We had tangents from A and E, and we have two tangents from P as well, right? Okay, wait. I should probably make the points. This point is T, and this point is R. So if you see carefully, you will see that because of, okay, let's go back to, you have sort of like the circle configuration that we did earlier. You have tangents and you have this, right? So you essentially get that this quadrilateral TREF is like -1, right? This is sort of the thing we did in the beginning. And the idea, you have -1. -1 is a good number because you could just replace these, interchange these. You would get like E comma EF. Wait, I just draw it a bit better. Yeah, you get EFTR is also equal to -1. So that's essentially the converse of the theorem we just used. You have that this is the tangent, and you know that this forms a harmonic quadrilateral. So you get that ATR are collinear, right? Get that ATR are collinear. How do you use this? Well, we still haven't showed that, we still haven't made much progress towards angle PIM 90, but yeah, now we can do it a bit better. Because we have, okay, we have other 90-degree angles as well. This angle is 90, this angle is 90. If you could sort of if you could somehow use any of those, it would be nice, right? Okay, should I draw a new diagram? It's getting a bit messy. Let's call this D. We defined the earlier thing. Okay, we'll find it as P. R. And yeah, this is what we defined. I'll just draw it in a different color. We want to show that this angle is 90 degree. Okay, so yeah, we still haven't used the midpoint condition yet. How do we do that? Well, we don't really have any usual synthetic way of using the midpoint condition, right? Because there is nothing like you don't have the power of appointing, defining other midpoints for midpoint theorem or Thales theorem or whatever. It won't be good. You could try it. You should try it. So as to get sort of an idea of what works well with geometry and what doesn't, what like what is killed by projective and what cannot be approached. But yeah, it's not really worth it. So we do what we always do when we see a midpoint, P infinity. Yeah. So how, where, what do we do? Like we have to pick a point to project from, right? We want to sort of pick a point to project from. And like, okay, let's try I. But if you try I, you can't really do much. Like there just isn't anything else to do with I. So that's not a good idea. You could also, okay, let's try A. Because if you tried A, um, okay, yeah, okay, A also doesn't really work because it's not getting anywhere at the 90-degree angle, right? Okay, this stuff doesn't really seem to help, does it? We have, okay, okay, wait, just a second. Yeah, nice. That's better. Yeah, okay, we have this 90-degree idea angle. By the way, if y'all have any idea, you should also say, rightly, because like, no, if you have any idea, you will get to know what works and what doesn't work. And so yeah, so what do we do? We have this 90-degree, this -1 thing. We also have this thing as -1. LDBC is -1. Okay, so it is already time. I don't know. Okay, yeah. So from here there is I'll tell you this. There is one sort of point where you project from to sort of kill the problem. I will leave it to you to figure out. But yeah, you have to use this M in some sort of way. Right. You want to use this in some sort of way, and like it's not, and in this case it's not really the -1 thing, because you can't project through, you can't, there is no point to project through, right? It's not this -1 thing. You have to use the fact that IM is perpendicular to this TR. This is sort of configuration. I think it's in Evans. um it's an EGMO. But yeah, okay, firstly you should try to prove that AT is perpendicular to IM, then you should use that to finish. I'll leave it to you as homework, I guess. Try to prove M. Okay, once you have that, then you can do some cross ratio stuff. But yeah, I think that's probably it for the lecture. If you have any doubts, you can say that. Yeah, thanks for attending the lecture. There are 6 people. Nice. I'll stop sharing my screen. How do I do that? Yeah, there we go.
Yeah. Also stop recording.
Yes, how do I? Okay, wait, where is the record thing? Is it here? No, that's the.
There's a button, just click it.
I didn't really start the. Okay.